Hey guys, how's it going? Welcome to another episode of Ferris Makes Emulators. This is episode 23, where I thought we would do some more sample extraction like we did last week, but this time with a different game in particular. So basically, a little bit of context. First of all, this is probably going to be a little bit of a shorter stream than usual, because today is a very special day in that at midnight, the Nintendo Switch is released. And so in about 4 hours, I need to get mine. And I have some preparations to do because I bought 2 units, gonna take one apart, gonna play the other one. Took tomorrow off, it's gonna be a great weekend. But I got some preparing to do. So that should be fun. But yeah. Anyway, last week, we went over the sample playback routine in Galactic Pinball. We made a lot of progress in actually reverse engineering this and basically thought we had it figured out. Of course, I later found out there was a small detail that actually wasn't correct. And I've been back and forth on this a lot because there's some weird stuff going on. By the way, Daniel Collin, Echonym, Soda Design, I'll comment Dark Second. How's it going, guys? So the main thing is that what I'm basically trying to accomplish here is I want to look at a bunch of things that use the timer to try and figure out how its implementation, how it works really at a deeper level than what all the documentation is giving us. And the reason why I thought to do this initially was because it was basically because of the timer that some sample playback routines in at least one game didn't work correctly. But as I think more about it, I think it's actually a pretty good strategy to just continue working on these specifically because they tend to be not terribly much code, at least to get a high-level overview of what they're doing. They also use the timer with very small intervals, which is really good. So we should actually be able to get some pretty significant information by measuring their timing and things like that. And it's pretty obvious to tell if they're wrong, which is where we started in the first place. So again, last time we did the sample routine in Galactic Pinball. So what we basically did is went in the debugger in the emulator and basically figured out how that worked. That was pretty cool. And then shortly after the stream, I ended up writing a program to actually dump samples from ROM. So they would actually decode that. And when I initially did that, it didn't sound quite correct. Let's see if I actually have a render of that so I can show you guys what that sounded like. I may have deleted it because it was the wrong sample rate, so I'm not sure if I kept it, but I'll see if I still have one of these. Yeah, it looks like I don't, unfortunately. But basically, it didn't quite sound right. The high end was a bit lacking and some other things. And I thought that was a consequence of the fact that I'm basically just sampling the data, not necessarily passing it to an audio emulator and then dumping samples from that, because that wasn't really the point. The point is that I want a wave file of the sample so I can sit there and adjust the the sample rate and figure out okay, when does it sound like it's playing at the right rate? And then what is the period of each samples? How much time between samples do we have? What are the settings of the timer that should give us that period? Just to basically collect all that information. Now, as it turns out, I actually missed a crucial detail in the playback routine that meant that I was reading in half as many I was reading the samples twice as fast as I should have been. So this is what the extracted sample from Galactic Pinball sounds like. Let me solo that. And apparently space is not working for Ableton. Hold up. Oh, there it goes. Okay. This was a bit quieter than I expected. Let me turn that up.
Welcome to Space World. Let's go. Welcome to Space World. Let's go.
So other than the fact that it's pretty ringy, it's basically correct. So what I have down here, this is the extracted sample. So this is literally after we figured out how it worked and after I, got it wrong the first time, fixed the errors, and then this is the exact wave file that's dumped from decoding the actual sample data in ROM. So that's what I have in the middle there. And then at the top and the bottom, I have 2 different hardware recordings, and they basically sound the same. So this is hardware.
Welcome to Space World. Let's go.
Not as ringy, but still kind of noisy. If you play them together, they're basically almost exactly the same rate, but you'll hear a little bit of phasing. You'll hear this like over the top of it, and that's because they're playing at very slightly different rates.
Welcome to Space World. Let's go.
Hear what I mean?
Welcome to Space World. Let's go.
Oh, sorry, excuse me. So the thing is, in terms of the actual rate of this sample, I'm pretty sure that the target sample rate here is going to be 20 kilohertz for a couple reasons. First of all, that's less than half the sample rate of the actual audio hardware, which means that we're below what's called the Nyquist. So if you have, for those of you guys that are unfamiliar with this concept, if you have like a buffer of samples that you're playing, which so basically the audio is laid out in like an array of samples, and they literally describe the position of the speaker cone as it moves across. And the rate at which that buffer is sampled is known as your sample rate, right? That makes sense. So basically your speaker changes position around, in this case, 20,000 times a second. So that makes sense. But the thing is that when you have like a given sample rate, you actually can't describe any signals above half that sample rate when you're using a discrete signal like this. Now, there's a lot of reasons why that I won't get into, and there's certain artifacts that you'll get if you try to, but basically you can't represent frequencies above half the frequency of your sample rate, which is called the Nyquist frequency. So if I say Nyquist, that's what I'm talking about. Oh, hey, Zach, how's it going? Jay Westfall, what's up? So the fact that I have this being extracted and then I just guessed at a sample rate of 20 kilohertz, because that's less than half of the audio unit sample rate, that means we should be able to output correctly. So that actually makes sense. Yeah, I'll also give a nice little simple explanation. Like if you imagine the highest value sine wave you could approximate with an array like this, you would have a sample at the top of your range and a sample at the bottom, and just alternating back and forth. And that would be half your sample rate, is the frequency of that sine. So that's as best as you can do. Anyway, so the fact that, the 20 kilohertz thing matches up there, that's really good. The fact that it sounds really close to the hardware is really good. And I also tried adjusting this with not really a few hertz here or there, but like significant jumps like 21 kilohertz or 19 kilohertz. And it was pretty obvious that this is about as close as we get. So ignoring very slight timing differences, which I think is basically okay for this, like my guess is that the hardware wanted to play this at 20 kilohertz. And then there's some, maybe adjustments that it might do, but we're just trying to get kind of a high level overview. So what that gives us, if you have a 20 kilohertz sample rate, that gives you a sample period of 50 microseconds per sample. And that's a problem because our timer at its smallest interval only ticks at intervals of 20 microseconds. Now, that's a problem because that means our 50 microsecond interval is exactly 2.5 timer intervals of again, the smallest timer interval that we have. So something weird is going on there. So what I did after I figured that out, so I got the timer settings. By the way, let me show you the code that made this different and why the sample format is a little different than we thought. Basically, we thought that it was like reading samples, and it had a couple formats for when it would set a different register other than the audio register, and there was also an escape code for ending the sample. But one of the things that we didn't pay attention to was this R10 value here. So we load a value from memory into R10. We compare it to 0. If it is 0, we're going to branch over this update routine here, right? Where we will also increment it and then jump back here. So basically, this is the code we're skipping. So we increment R10 and then skip this. Now, you'll notice that this is the thing that will grab the next byte from the stream. And, or actually, it will shift left the current byte from the stream, output it, and then, it'll shift left the current byte from the stream by 4 bits, and then it will add 1 to the sample pointer, right? So then it will increment the data stream pointer. And then in the next time, so if that were not the case, or after this happens every other time, then it will actually, where did that go? Here, add 31 R10. Now, the interesting thing about this 31 is that this actually gets sign extended. So this is actually -1. So what we see here is that every other sample that's output we will either take the value basically as is and dump it in the register, or we'll take the value and shift it left by 4, and then put it out in the register and then increment the pointer. So that's where I got the thing wrong, is that basically I wasn't doing that sort of swap thing. By the way, this is the code that I wrote, just threw together to dump the thing to a sample. I also have this on GitHub. Let me pull up the links to those gists just to share those. So here's the notes. And then here's the Rust implementation. Hey, John Hunter, how's it going? I know I'm kind of jumping around here. I'm a little scatterbrained right now. In fact, I also forgot to record again, so I'm going to start that now just in case. But yeah, really excited for the Switch. Anyway, so this basically does like the simplest possible wave dump we can have. I've used this code a few times, like it's laying around in the Rust Boy repo as well. And this is the actual decoding routine. It says decompress, but that's because I also ripped this from some other code that I wrote for something else. I like doing these just tiny programs that just like dump whatever data. But in particular, it was this value here that we didn't emulate properly. So here, it's just a value that flip-flops between 0 and 1. I didn't use a Boolean because I didn't know if it were going to do other values when I initially wrote this, but this is basically all the logic that's there other than actually outputting the sample. And a couple other notes, but it's really, really super straightforward. And yeah, Cryderion, if I'm saying that right. Yeah, this is Rust. If you do, whoops, that was not what I want to do. If you do bang lang, then it'll tell you. A bunch more of that info is in my FAQ, by the way, below. So yeah, so that's the thing that extracts the sample, and it's basically just dumping a bunch of bytes. It ends up being a 20 kilohertz mono sample. And I also dumped some of the other sample data as well. This is kind of a control, and it does work. So yeah, so that's what we missed. That's how it works, and it was a pretty easy fix. And then again, with adjusting that sample rate, so I tried first adjusting it on intervals of our small timer interval. And the thing is that the closest you get to around 20 kilohertz when you adjust that interval based on those, because it's either 10 microseconds less or 10 microseconds more per sample, you actually have a pretty big variance of the sample rate. So after 20 kilohertz, you get down to about 16 2/3 kilohertz. And then above that, you get up to 25 kilohertz. So it's definitely not those. Yeah, so that'll be pretty cool. John Hunter, yeah, I'm pretty pumped for the Switch. My plan is to, so I bought 2. I'm going to take them home. One of them I'm going to take apart, post some board shots to a Discord group I'm part of. And then I'm going to use the other one to play Breath of the Wild all weekend. It's going to be great. Yeah. So one thing I did is after I basically verified what I think that sample rate's supposed to be, I looked at the timer to see, like, basically play with the implementation to see if I could actually get it to match. Now, again, because the sample period is 2.5 times our smaller timer tick, there's something really weird going on to actually make that happen. So the timer has this reload value, which in that case is set to, it's set to 2. So the timer will count down, and then an interrupt will be raised, and then it will reset at that number, and then it will count down on this small timer interval. So if we let it count down twice, and then somehow get half of that interval as well, it should work out to the same period. Now, one of the things I did was I started, like, just by hand kind of estimating cycle counts for the playback routine. So I basically just looked at some of this stuff and was like, oh yeah, that's like 4 cycles, whatever. I'm just rattling off some numbers. So that's basically what I did and counted them. Because what happens is the timer ticks. We basically have a branch. Here, there's like a very small amount of code, like that should be insignificant compared to the sample period that we have. And then here we reset the timer. Now, what's interesting there is that the timer is disabled and then re-enabled. And I'm guessing that the disable and re-enable, like, resets some internal counter. I'm not really entirely sure the details yet, which is why we need to do more digging. But basically that will sort of offset the small timer interval. So I played around with an implementation in our emulator code to see if I could get something that would play back this sample correctly. The idea is I want to do this with a few different routines, again, just so I can compare, and then hopefully all of those will shed some light on what's actually going on. But I ended up just kind of throwing together a little hack here that basically whenever the timer goes from a disable to an enable state, it will basically delay for 7.5 microseconds. Now, that number came from a bit of trial and error, and again, I know this is totally hacky, but I just want to see if I can get it to work doing something, just to see if we can shed some light on what's actually going on. So that ended up actually being able to play the sample back pretty accurately, and also didn't seem to break anything else, which is actually pretty nuts. In fact, it even started making some other games work a little bit more consistently. Like there's Nestor's Funky Bowling and Golf that basically crash randomly at different parts in the game. And the fact that this actually kind of made those seem a little more stable is a bit unnerving because a delay like this wouldn't actually make very much sense. So I'm just going to go to the sample so you can hear what it sounds like with this hack.
Welcome to Space World. Let's go.
It basically sounds correct, right? So that totally works. Also, we still have a bunch of debug printing here. So that's I think that's a step forward, even though it's a hack. So I just stuffed it on a branch. And then right now I want to dig into another sample playback from another game. In particular, there's a few games produced by a company called T&E Soft. And a lot of these games in their intro have a little T&E Soft logo and a voice that actually says T&E Soft. So this is what it sounds like.
T&E Soft present.
Now that playback rate is, from what I can tell, correct according to the hardware. I don't actually have a recording of the hardware in Wave right now, but just from memory and hearing it, it really sounds correct. And depending on how I adjust the timer implementation, it's very easy to mess this up, very easy to make it sound wrong. So for example, let's see if I can reload pending. Yeah, I don't really want to dig into how I can make it sound wrong. I want to dig into how it actually works. Because basically, if you make it take one less tick, then it will sound too high pitched. If you don't have what was one thing? Yeah, if I add another condition to disabling the interrupt and or disabling the zero status, because I found a line in one of the pieces of documentation that basically says that when you're writing the control reg of the timer, you can't actually write the zero enable. You can't disable the interrupts and disable the zero status, or maybe it's you can't enable the interrupts and disable the zero status. It was a bit vague, but if I add a conditional to try and make that happen, the thing will actually play too fast, if I recall correctly. So there's a few things in here where it's we kind of have to match the docs and really look at what's going on here. This is the kind of thing that would also be, I think, kind of difficult to write hardware tests for, because a lot of the times when you're doing timing tests on the hardware, you time things against the timer. Now that's a problem when the thing that you're trying to test is the timer. But I mean, I think it should be possible to do if we can predict how long a certain loop is going to take, we can start making our own timer that way, as long as it fits in cache and it works really deterministically. Then there might be some other ways that we can do timing tests, but we'd have to get pretty clever. And again, I don't have that hardware right now, so.
T&E Soft present.
Okay, so that logic actually didn't affect this game, so that was probably for something else. Anyway, so this is the whole hack right here, where it just resets the counter, and this ends up being between this value and then 400 cycles, this ends up being 7.5 microseconds. Again, total hack, but I think it's progress because at least we found some more information. But again, what I want to do is I want to dig into this other sample playback routine and see how it's working. Now, I did start a little bit of this. By the way, one last thing before we dig in is the kind of data that I'm trying to get here basically looks like this. I really want just a super high level overview of how each of these play routines works. So for example, the Galactic Pinball one, the timer reload is set to this value. Timer interrupt fires every 50 microseconds, which again shouldn't make sense, but that's what happens. Basically, right after that fires, we store this value in the timer control and then store this value. And then we output the volume to these two registers. And that basically repeats. That's like the highest level overview you can have of the sample routine. So I'm basically trying to get that high level overview for a bunch of different sample routines. And then as a control to make sure that information is actually correct, I want to actually extract the samples from the ROMs as well. That's also because that's pretty fun to do. Now, I did actually start digging into these T&E soft games. In particular, that was Red Alarm that I was showing you there. And I basically got as far as to find the routine itself, which this is right here. It's just the timer interrupt. And then I just dumped a bunch of chunks of assembler. And you can see the code is a bit longer here, but I've already started to sort of comment in some things like certain register values. So for example, right here, we can see that it's actually loading R11 here with this value, which is where the system control registers start. Here, it actually doesn't disable the timer interrupt, and then enable it. It actually just writes one value here every time, which is fairly interesting. Or maybe I have that wrong because it's been a few days since I looked at this. Yeah, here we go. So it actually stores another value here, which is also the same value as this one it stores here. So I think it actually, all it does is disable the 0 interrupt, and then later it'll re-enable the interrupt. So in this case, like, it's not stopping and starting the timer again, it's just disabling and then re-enabling the interrupt. So that's like one significant difference. And find that the actual sample period here ends up being a multiple of the small timer interval, because that's what we expect to find. So that was one thing I found. I also noticed the like here it loads R4 with the start of the VSU registers. And then, for example, here, if you end up, that was R14. Did I say R4? I meant R14. And then if you look at what these offsets are, these are specific addresses to these voice registers. So for example, here we're writing the voice 1 through 5 envelope data from whatever R21 is. So this seems to basically read a value and then just store all the voice envelope data from here. Of course, later I found that there's a bunch of these chunks here that are storing voice volume for multiple voices. Now, I don't really care too much about extracting the full sample, so there might be some weird stuff that's going on with where it's like trying to use different voices to like add different chunks of different waveforms, and I'm not really sure why it would do that. Like, we'd have to really dig into the data to figure that out. What I'm mostly interested in is the rate of the samples. So if we can extract like enough of the sample so that it's like we can tell that it's playing at the right rate and that it's like we've read the data correctly enough, then I'm going to be happy enough, basically. And then we just, again, want to basically figure out how it's interacting with the timer, what it's setting up the timer to, like what its settings are, and then again, that sample rate, and that should give us the information that we're after. And I want to do this again for this one and hopefully a couple other titles as well. But yeah, I think that's all of the overview since last week. So I guess we can get started. However, I actually have to use the restroom, so I will be right back. By the way, I just realized that I've been mentioning this Discord group that we're hacking the Switch on a few times, and don't think I ever posted the link. So here's the link. The link that's to a wiki that we're gonna maintain. But I think the Discord link is in there somewhere. I'll probably link to that as well. Contribute Discord. Here we go. There's that. That's reswitch.tech, in case I forget to link it in the YouTube thing. But yeah, that should be pretty cool. Anyway, back to our sample fun. I am scatterbrained today because I'm excited about that. But yeah, so here, the timer reload is set to 0004. So that's like twice the rate as our other one, at least in terms of the timer settings. So that's why I said timer in fires every 80 microseconds here. You need to double check that. I was actually outputting, though, a bit of timer information. So, for example, let me pull it up again. And I'll change my terminal font. There we go. Oh, whoops, I skipped it. All right, here we go.
T and E saw present.
Now, I cut it off at the end there just so we made sure we actually got this. So yeah, it's basically saying the timer reload is 4 and timer reload fire, and then we adjust all these. Now again, because the timer isn't disabled and then enabled, I actually think that it is going to be 80 microseconds. But yeah, just have a note to double check after we've extracted some of the sample data. So I want to try and dig in what that might look like. Now I'm not really sure. So our 4, I believe, is our globals pointer. Oh, Dark Second, you're working on a JIT. That's awesome. Is this just to play around with this stuff, or do you have a specific project in mind? Always want to talk about JITs. Yeah, so I think R4 is our global pointer. And I'm guessing that's what's happening here. Let me set a breakpoint here. Or actually, yeah. By the way, this, just to break down what this was doing, so this is where the interrupt actually jumps to. And as usual, that would basically, here, adjust the stack. Make some room on the stack, load the address that we're going to jump to, and then actually jump there. Once we're there, interrupts are disabled, and then we basically jump to this routine after saving like a couple registers. And then when that returns, we're going to clear the interrupts and then return from the interrupt there. So this is basically the top level stuff, and then the routine that this actually jumps to is this code here. So that's what that top stuff is. I'm leaving it in these notes just in case we need to start doing cycle counting, but basically they're not that terribly important. This is the address we really want. Dark Second's just doing a JIT to play around. That's awesome. It's really, really cool. So let's go ahead and add a breakpoint here. Now, this actually fires, I believe, if we just add the breakpoint there now, this should fire basically all the time now because there is still the timer interrupt firing here. But I'm guessing that we'll hit a different code path when the sample's playing and when it's not, just like we saw with Galactic Pinball, because they're going to want a really tight like sample playback loop for the timer here, but then they're probably going to have a smaller one, or one that happens a lot less often. In this case, this uses 100 periods. Yeah, that's probably going to happen a lot less often. Ooh, Dana Collin, not related, but super cool nonetheless. Deploy noise WordPress, slides, Insomniac Games, Cacheism, or Cache Sim. There we go. Ah, Cache Simulator. That's actually super funny. So I've been reading a ton about caches in that computer architecture book, and just learning how they work generally. And that's actually totally something that I think I wanted to write if I'm understanding what this is. Yep, it's a cache simulator. Oh, that's really cool. Oh, Dan Collins says it's way more than that. I'll have to check that out more later then. They trapped the CPU also. Ooh, really cool. That sounds really sick. So I just wanted to step through these. I want to look at the registers because R4 is, again, what I suspect to be our global pointer. And judging by those offsets, this basically makes sense. Because 0500 is our RAM, so like R3 you can see is our stack. R2 has never been used. That's what dead beef in these registers means. Because they're undefined on startup, so we just fill them with dead beef. So that is cool. And yeah, so we want to look at the offsets from here. So for example, this first value that it loads, 32690. I'm bad at converting those kind of numbers to hex in my head, so we're going to pull this up here. Seven FB2. That seems weird. Did I do 32960? I probably did. Because it's 690. Oops. It still is 7 FB2. Oh yeah, of course. Whoops. Did it again. Okay, that's more like we wanted to see. Now Danny Collins still haven't installed the console calc on the Windows PC. On the Windows machine. There we go. Words, man. So what I want to do is just dump the memory here. Does that cover 4E as well? Yeah, it should. So this is the number we're reading, apparently. Now, what I'm going to guess is that one of these first values that it reads. So, for example, it reads that and then ends it with 1. If it's not 0, it jumps to one thing. Otherwise, it checks a different bit and then jumps to something else. Now, if we look at some of these addresses here, this goes here. This goes right before that and then jumps to something else. It's actually way out of the range of what we're looking at, so that's probably not particularly relevant. But we'll have to see. But let's go ahead and step this and see what happens here. Also, it discards the result here, so we can't actually check what that was. But we can check what the result of the branch is going to be. So that should have been 0, so I think it's going to skip this, which it did. So that makes sense. Going to check a different bit, which should also be 0. So this actually will take that branch. And then it goes outside of, to that other code. What I want to do really quick here is, whoops, that was breakpoints. I want to continue this and get to where it plays the sample and see if that value is the same. And then see if that stays the same. Because I'm trying to like eliminate code we don't care about. And I'm guessing there's going to be, I'm guessing a lot of this is code we don't care about. Which is kind of why I want to look at these sample routines. Oh, that beautiful sound. I'm going to save you guys the trouble and mute that. Okay, so now we want to set this breakpoint again. Oh, whoops. Did I not do that quickly? Oh, I did 25FC. That's fine. We can just reset. So here, all right, so if I just look at that byte here, it's now 1, which is basically exactly what I thought it might be. So that's pretty funny. Now, what I want to do is I want to hit this a few times and just see if that basically stays the same. And it does. Now, I'm going to do that a couple more times. Okay, this still stays at 1. And then what I want to do is we're going to remove this, continue, wait till it finishes playing the sample, hit it again, and there it's back to 0 again. So my guess, oh, I'm sorry, I didn't realize this was right behind my head. I think it still should have been visible, but yeah, so what I think that is basically whether or not it's going to play the sample, just like we saw in Galactic Pinball. So under that assumption, I'm going to start splitting up some code here. In particular, this jumps to this routine here and then carries on. And this actually makes sense because, as you can see here, we looks like we preserve some registers, and then here we start loading like the timer stuff that we saw earlier. So this is probably the sample routine that we actually care about. Which is good. That means we've eliminated a lot of, well, potentially a lot of code that we don't necessarily care about. I'm also think I'm going to like comment all this out. I wonder if I can just do Control Shift. No, it's Control Alt. Let's do that. Just to kind of get that out of our heads. I could remove it as well. Yeah, let's just do that. Yeah, Colin, I would assume that the sample routines would be fairly similar. I'm hoping so. I'm hoping there's small differences in how they use the timer. But in terms of like what they're putting to this to the VSU, they should be pretty similar. And the structure should also be pretty similar too. Like we just have this timer that ticks and then just dumps sets some registers in the VSU, and then yeah, it should be a pretty simple loop. So I'm hoping these will be insightful enough. So we can basically ignore, I'm guessing this is also signed. So I'm guessing we can basically ignore all this because that's just preserving some registers. Here we adjust the timer stuff. Looks like we have some more registers or some more values here. I also kind of want to see if we ever see this value again. Because if we see it here, for example, here we load it. The reason I'm looking for this is I want to see if we store it anywhere, but it doesn't look like it, at least in this code. The reason I was looking for that is I wanted to see if there was like an escape code for stopping this, for example. But may not be in the code that's visible to us right now. Could be in something else. But, I mean, we can get to that as we dig into this more. Probably going to be jumping around a lot, but just want to take a lot of notes. Looks like also we store... Okay, so another thing I did in the disassembler is there were a couple instructions where the like left and right order of the data flow wasn't actually correct. So I went ahead and I also fixed some of those. So I'm guessing, yeah, so that makes like this easier to read. For example, like this store system register will store from the system register into one of the general purpose registers. That makes that a little bit more explicit. But it still looks like really this is probably just preserving these values. So for example, if we look at this, if we try to find this elsewhere, here we go. Yeah, we see exactly the opposite. So that's just basically preserving some stuff. And that's good because this is like, you can see that this is basically cleanup here after doing the routine. Also, there's some branching here where this branches over this and then this goes somewhere else. Who knows where that goes? Although this is R16, wasn't that set near? No, maybe I'm here is what I was thinking of. But is this the same R16? It looks like it is, actually. So the reason I'm looking at R16 is because, like we saw with this value for whether or not we should play the sample, it looks like that gets loaded into R16, and from what I can tell after that, at least in the code that we have visible here, R16 never actually changes. And the reason why that's significant is because it does look like it ands it with another one of the bit masks that we saw before, and then we'll branch to some other code, which is down here. So I guess one of the bit masks, one of the bits in there determines whether or not we write to all these voices. Otherwise, we just write to a few of them. That's kind of funny. But I think it's also something we can probably ignore. So what I want to do, I want to just kind of assume the simplest thing possible. Now that I think about it, and like, so this will write whatever's in R21 to this. This code, by the way, it basically loads a byte here from R25 with no offsets into R21. It then moves that into R22, shifts it left by 4, and then ORs that back together. So if you assume that the sample is going to be a 4-bit value at this point, it basically copies that, shifts it left 4, and then ORs it with itself again. So it basically duplicates the 4 bits, the lower 4 bits to the higher 4 bits. And that makes sense when it's writing one of these volume registers, because these volume registers are stereo. And I don't remember which is which, but one of the 4 bits, one of the sets of 4 bits is the left speaker volume, and then the other one is the right speaker volume. So that's basically just copying the 4 bits to, yeah, the other left or right. Daniel Collin, random question. Are you going to Rust Fest? I had not heard of Rust Fest. April 30th. Probably not. Because our company has some stuff happening around that time. Gonna be pretty busy. And that's pretty close to after revision as well. But wasn't there like a Rust conference in like September last year around in Europe somewhere? Or was that in the summer? I don't remember. But could look into going to that. Just got to plan a little bit more ahead. So what is R25 at this point? Actually, wait a minute. I was totally printing. When like anything changed in these registers. Just wanted to see if it's like always writing all 5 of these to see which of these values we can actually watch. Oh yeah, Rust Conf was in September. Yeah, that was in Portland. Whoops, I skipped it again. Again, gonna cut that off. Yeah, it looks like we're basically always writing these values. Although they don't always seem to change. That might have just been at the end of the sample, though. These really don't have a lot of variance, which kind of worries me. Let me run that again. Here we're seeing more variance. Maybe not as much as I would have liked, though. This one may not be as simple as the other one. Interesting. But I think a decent strategy might be to try and just dump one of these voices, just these straight volumes even, just to see if it even sounds similar to the sample. Yeah, I know what you mean, Daniel Cullen. I think what this is doing is probably setting. It probably has some data in the waveforms that are playing, and probably tries to mix those with some values or something, which is really odd. I wonder. Should probably dump the values that are going into the sample memory. But I mean, so if that were the case, then just dumping out the volumes, like picking one of those voices and dumping the volumes, should actually get something that kind of sounds like the voice, I would hope. But it might not. And this, I believe, yeah, this is all the VSU writes that we actually see. So nothing else is happening while the sample's playing, at least. Now, one of the things we can do here as well, though, is we can set a breakpoint for the actual sample playback routine, which we now know is here. And just see if we can see when it writes to those tables. Like, see if we see a dump of things that it wrote to the waveforms. Yes. Or maybe not. Yeah, this just looks like voice registers again to me. Very strange. Let's see what these actually are. Whoops. So they're basically in ascending order. 4018. Okay, yeah, these are offsets into the wave there. 4018, and then 4058, and then 98, D8, and 518. That's just D8, and then 518 would have been. Yeah, there's the other voice. And then 404. Yeah, so this is just some initial values like volume and stuff. But these first ones, this is actually pretty interesting that it wrote basically all the wave offsets to 0. So that means they would all be reading from the same wave memory. Just fairly interesting. You know what? Here's another thing I think we can try really quickly. Just to kind of get an idea of what's going on here is to mute a lot of the voices. That should be easy to do. In fact, that should do it. This is the kind of stuff that it would be like, could totally add debugging features for this, but sometimes it's just easier to just change the code. So I want to see what this sounds like. And if this sounds kind of like the sample, like if it's recognizable, then I think we can just focus on extracting just the one voice. Yeah, that was actually recognizable, I think. Just out of curiosity, though. I want to see what some of these other voices sound like. Kind of curious how this is working. That's pretty interesting. Oh, did you get? Oh, yeah. Sorry, I had my system audio muted. Sorry about that. Let's hope the second voice does something neat. So it sounds like one of those crappy ghost recordings. But this is fairly recognizable, I think. Let's hear it again. I'll turn it up a little this time. That's clear enough, I think, for this to make sense. But so the reason I'm kind of procrastinating, like actually digging into the sample data itself, is because it looks like there's a lot of juggling between these registers. And in fact, here it's even doing division. And that may not be that nice to step through. But the thing is that we found out that basically if we just were to figure out all the values going out of here, what am I thinking here? Basically, if we just figured out like the output of one of the voices, we'd get something recognizable. The next test I kind of want to do is to see if I can freeze. Is that Tomco? Thanks for the follow. What I think I'm going to do is see if I can freeze the phase of the voice so that it's not actually playing like sample data that changes over time, but that it's just like constant. And again, I'm just trying to see like if we can like maybe hack the emulator to just dump all these register writes, for example. You know what I mean? Try and dump something that's a little easier than necessarily digging into the sample format. Because again, if we can figure out the way that it interacts with the timer, and then the rate at which it's doing that or it's expecting to do that, and then we can verify that by making a WAV file. Even if it's not perfect, I think that's good enough for what I want to achieve. So I think if we go to, where is it? Standard voice with the phase here. And we should just be able to not adjust the phase. And that should basically make sense. Yeah, so that I think was a success. Just to maybe try one more thing. I'm thinking if we can basically just dump, like freeze the envelope value as well, which I'm guessing we can. And again, the reason I'm thinking all this is because if we can just basically dump all the values that are going into the volume registers, we should get something recognizable. And that'll help us get the right rate. If I remember the range of that correctly. The things you can do when you just let yourself make a mess should save us a lot of work. Yeah, that sounds about the same to me. So then it would make sense if it's like using all the different voices to like basically do DC offset and then change those over time. And it probably uses the different volumes of the voices to like adjust. Like one of them is probably like different amplitudes of the waveform. Not really sure. But that is something that could make sense. Basically using the different voices as different steps in like an ADC or something. I don't know, it's really strange. Actually, was there one more thing that I wanted to try with that or not? Yeah, because we know the phase is not changing over time. We know the envelope is not changing over time. What else could change over time, basically? Is there anything else? Yeah, I'd guess that'd be to get better playback quality. It's just like I think it's kind of weird that they would do that over multiple voices, but I guess it's to have like because if you just do one voice by changing the volume, you're only going to have 16 levels. So I could imagine it'd be a way to get more than that. Because the internal audio mixing is done at, I can't remember how many bits. More than that. More than 4. So it could make sense to just do different levels of that. Just trying to think of anything else that might actually change here, and I don't think there's really anything. The envelope should be fine. Volume is what we're modulating. Yeah. No, I think we're actually pretty good to do this. So then, how do we want to hack the emulator to dump the data we want? Is always the question that should be asked. I'm thinking that we can probably have it dump Chicken Falls. Oh, Chicken Falls. What's up, man? There's a guy I work with who's his name is Bundahagen, which is if you directly translate that into Norwegian, from Norwegian to English, you'll get Chicken Falls. That made me laugh. Chicken Falls says, I think someone got pranked today. And to that, I say, I think someone got disappointed when they actually went to Complete and couldn't get their Switch today. Wait, I wasn't supposed to admit that I knew that. Yeah, some buddies of mine got shipping notifications for their Switches earlier today. And they, apparently they went to the store. Oh, no, sorry. Bundahagen is Farmer Garden. Yeah, Chicken Falls is where he's... Yeah, is the name of a town in Norway. That if you directly translate it, it's his Hønefoss. So, yeah, I forgot about that. Daniel Collin on Amiga, we do a similar thing to get 14-bit output, even if the hardware is only 8-bit output, by merging audio channels and using the volume of one of the channels as the lower part and the other is the high. It's not 100% accurate, but works. Yeah, that totally makes sense. That absolutely makes sense. Delta, I was not at first interested in the Switch, but now that first stream stuff links re-switched, I want one. Cool. It should be fun to hack on. Cool. Yeah. Oh, that's what I was thinking of, was the frequency. But again, if the phase didn't change, the frequency wouldn't matter. So yeah, we already locked that down. So we know that if we just dump all the volume values that are coming out of here, we should be fine. The only thing I'm thinking, though, is that we don't want to necessarily do that unless the sample's playing. So I'm wondering if I just want to run this again, and I'm going to get rid of the timer printing. And what I'm going to try to do is just see if we can basically dump all those register writes, which should work as long as there's not too many extra ones happening. So that's what I want to just print and see what happens. Right, so we had some bytes here, which I'm guessing, yeah, these addresses, this is all waveform memory. So we're seeing 3F here, by the way. That also kind of confirms what we're thinking of, what we're talking about there. Yeah, it disables the sound. And it doesn't look like it hits the registers again, probably until... Like, it might output a couple zeros there, but that should be fine. Oh, skipped it again. Because if we have a couple zeros at the beginning of the extracted sample, that's not going to be something we need to worry about. So if it basically just dumps those registers and then does like nothing for a while, then we can just dump all those to a file. Cool. So then what I'm thinking is that now that we'll have this, I think I'll just hack the emulator to dump a bunch of these to a file. And then I think we can write another small program to stick a wave header in front of that. Or we might as well just take the wave code we had anyway and just like hack it in here. Because I can always just stuff this on a branch. But yeah. So the way we'll do that is pretty simple, I think. And we'll just go ahead and let's just add a file handle here. Just gonna look up some docs on what the type of this is gonna be. That's just a file. So we'll just hack this in here. Why not? We know we at least need that. And then we'll just do this. And this will be cool because then the emulator starting and shutting down will close our file handle as well. Let's do this in case we want to do other stuff here. Call it .bin until we actually stick a header in front of that. Also, we'll unwrap this because we do not care about errors for this. Im something. Im really long name I can't read. Yeah, this is Rust. All right. That should get us our file. Let's just run that really quick. So if you get any errors, we shouldn't. Yeah, that looks good. And then we actually need to dump the data. So I believe to write a single byte, we actually have to output a buffer. Let me double check that. And I know I'm not showing the thing on screen, but it shouldn't really matter much. So what we're going to do is we want to know the wave voice 1 volume was the right one, I believe. So it's going to write the volume reg, and then we're also going to, yeah, we'll do this. Just make an array of the value, and then we can file.write all, and then we should be able to give it the buff reference. We'll unwrap the results, and that should be it. I did mean self.file. Thank you, Rust. Why don't you code an ASM, mate? So weak. That's funny. That is funny. Ooh, you can in Rust. All right. So that should have dumped our binary file. I love making these tiny little programs to do this kind of stuff. I think it's really fun. So where did that go? That would have gone in here, I believe. Yep, so there's an 18 kilobyte dump.bin on my hard drive. And this looks like the values we were seeing. And also, if you notice, if you look at the data, T&E Soft presents. There it is, yeah. T&E Soft presents. See what I mean? And that explains why we saw a lot of the same value at the end, because there's a bunch of basically silence. It also writes a 0 at the beginning and a 0 at the end, which I'm guessing is when the sample started and stopped. We can just remove that in the hex editor. Don't have to, but since we can, let's just do that. And then, so what I'm thinking is we want to take this data and actually attach a wave header. You know what I actually want to do? I'm actually just going to copy the code for the wave header that I had before that, and just dump it again. Data Colin, I think this data looks weird. I also think it looks weird, but it does look like it'll do kind of what we expect. At least to have something that sounds like a sample. And that should be good enough for now. So yeah, we'll just copy these functions. So design, shouldn't it be more random? I'm guessing the other channels would be a lot more random. Like it looks like a weird sample format, but again, I think because these are shared between the different voices, I'm guessing that it altogether it would look, we would have a lot more high frequency information in other channels. That's my gut feeling as well. Why 22? I'm not sure. I don't know. But I'm thinking it's going to be quicker to just dump this WAV file than try to understand it too deeply. Like, I think we'll get what we need out of this without having to do that. Because we know what the timer settings are, so we know what we should expect the timing to be. And if it seems to be correct from this dump data, then I think we've gone as far as we need to. Okay, so I was going to get the rest of this stuff here. Oh yeah, this also... Oh yeah, this would actually just fill a buffer and then dump that data. Let's actually do that too. Fill a buffer and then just dump that. Rather than having the file here. We're going to do dump data. And then what we can do is this. Oops. Oops. We want to here. Oops. And then to close the file and everything, we'll just implement will drop for the whole thing. Sweet. And then we should basically just be able to copy all this. So hacky. And it will work so well. We don't need any of this here. We don't need this. And then this will be, don't need this. We're gonna, so I'm actually gonna make a guess the first time, and if it sounds like we expect, then we're good. I'll leave the hello world here so that we can see when it's done, and and see that it actually worked. And then, yeah, this is an output, but this is actually just gonna be self.dump data. So we have the file and the writer. Cool. And then this will be tsoft. And okay, so we know that based on the timer settings and the fact that it doesn't reset the timer, I'm guessing the period is going to be 80 microseconds per sample. So if we go into our calculator here, if we take, what was it? I think we take 1 second in microseconds, which I believe is that number, and we can divide that by 80 microseconds, and we should get 12.5 kilohertz. Now I think that makes sense. So let's just do that. And everything else should make sense, except I don't necessarily want this shift here. Don't think I want that. We'll just do this, and then it might be super quiet, but I think we're just going to be okay with that for the first dump at least. And if all that works, which it didn't because we didn't get I/O, because we need to grab self and write. And we got buff writer, which I believe is also in here. And bits per sample we don't have right now. And then we can't move out of dump data. Let's clone it. I love doing hacky stuff like this sometimes. Sometimes just being resourceful and making a mess is the best thing you can do. And we got the hello world, so that should have worked. Now we have a 36K file that says T&E soft. Okay, this was funny. So you probably couldn't hear that because it was really quiet. So let's go ahead and I'll dump that again and I'll add a couple shifts. This, I'm guessing we can get away with like times 8. Actually, we know that the value was 2, right? And then that's basically going to be unsigned. Or I think it went up to 3. Let's just try that. Worst case is it gets distorted. But the fact was it was really high pitched. That can mean a number of things. Now, I'm not surprised that it was quiet because basically what it's doing is if it outputs to the voice volume register, that's basically the same as also multiplying it by the wave output of that voice. So that's what's going to amplify it in the actual system. The high pitch thing, that's a little more concerning. That's a bit concerning. What I'm going to do is I'm just going to adjust this to like some other sample rates that might be sane. See what we get. Oh yeah, it didn't call in. It should be 4-bit. I was thinking of the actual values, but I think the values go into both bits of that register. So we should actually just mask it off and shift it, but this should be okay. If I have to adjust the sample rate again, I'll do that. All right. Interesting. So we do have to adjust that again. So I dropped it from 12.5 kilohertz to 10 kilohertz just to see if that would work. Also, let's go ahead and fix that sample. So we knew that this was 4-bit, so we can... that'll mask off the 4 bits, and if we only have 4 bits, then we should be able to shift it left 11, because if we do 12, we'll get sign. We don't want that. Yeah, 11 plus 4 is 15. 0, 1, 2, 3. Yep, this should make sense, I think. And that'll probably be really loud. I'm actually going to probably pull it into Ableton before I play it, just in case. let's make a new track here in Ableton. And do this. This is the data we just got out. That still seems super quiet. That cannot be the same data we just pulled out of there. Weird. If we turn off warp here, I'll just pull it up here. That's strange. Because I would have expected it to be a little bit louder. But it could just be that the values we saw were only like 1, 2, and 3. So it probably does actually make sense. This probably is correct. But I'll leave that for now because we can always adjust that in like Ableton. I think that that's okay. We are getting something recognizable again, so that's nice. But it's a bit weird that this is so fast. So that was 12.5 kilohertz was assuming that we had an 80 microsecond period. Let's say if we had 80 plus 20 would be 100. If we had 100 microsecond period. Now I'm pretty sure that that gives us 10 kilohertz, and that's why I tried this. But it seems to be a little bit longer. So let's just try what it would be at 120 microseconds. And then we get 8333. Now the closest we can get to that is 8333. Daniel Collins says, can we test dump another voice and then compare them? Yeah, that's a good idea as well. Because I think it did write these every time, but it'd be a good idea to write out some of these other voices as well, especially to see if the volume thing was working as we expected. And it should be basically trivial. Now that actually sounds a little bit too slow to me. Just gonna run this one more time just to hear them side by side, basically. Oops. Oh, keep skipping it. I'm used to trying to go into the game to test that it works. I just skip right past the stuff. Okay, actually, that sounded really close. I think I was just hearing a little more low end than I thought, but that actually sounded pretty correct to me. What I should probably do is do a recording from the hardware, but I actually think we basically got it here. And that actually kind of starts to match up with some of the other timing things we've seen where we get a couple extra periods, even though the timer reload is 4. And the fact that this is basically exactly the sample rate we should have gotten with 6 timer periods, that's a pretty good sign. I'm going to go ahead and dump that other voice as well. I think that dump another voice to see how that sounds. Just going to comment that out. We'll do the voice 2 volume, for example. While we're here. Oh, I think this stuff is cool. So now we can look at those 2 voices together. Oops, that loaded them. Not the way I wanted to. Here's a cool thing. This is voice 2 versus voice 1. Let's see if we can get a even better view on these. Going to add some gain. Okay, we can go up to like 10 dB here. Which actually that'll clip when playing them together. Let's do like 8. Still might also clip, but should get us something we can see a little bit better. We see some differences here. This is the kind of difference I basically expected to see, though. Except maybe that these would have been at different volumes. But the kind of variance we're seeing here looks pretty correct to me. It sounds a bit fuller playing them together, and I'm not sure if that's it just being louder. I mean, we could dump the other voices just as an experiment. I think that could be kind of fun. At least to dump another one. Because it's so easy. Oops, we want to make sure we don't overwrite that other one. Oh, I still create a file here. That's funny. That was in drop at the bottom, wasn't it? Yeah, here. Okay, so that'll give us the third voice. Make a little room here. Yeah, you can see the variance here.
E and Esau present. E and Esau present. E and Esau present. E and Esau present.
Yeah. So I'm thinking these are just added together and they probably have different voice volumes. Or, yeah, they probably changed the voice volume with the envelopes or something. Or maybe it just adds all 5 voices together. I mean, why not just check that? Because we can. We only have 2 more. And then the noise voice, but I don't think that's contributing. In this case. Did I change the file name? Yes, I did. And then we'll do voice 5. That one seems noisier than the others, but maybe that's just in my head. Let's see if we can set this up to be a little nicer. That's the Space World one. Let's dupe this again. And this will be number 4. By the way, need to disable warp on all these. which I hope, because they should still end up at the right rate here.
He and Esau present. He and Esau. He and Esau. He and Esau present.
Oh yeah, this is definitely adding different like octaves or different levels of noise for all the different channels. Because you hear how like smooth this one sounded.
He and Esau present.
Yeah. I'm gonna adjust the volumes of these as well, as we don't want to blow the speakers. And I'm not sure if these are all supposed to be at like the same volume when it's actually playing back the thing. We could look at the volume or the other voice registers when this is happening, but this should be good enough.
He and Esau present.
Or they are just played at the same volume, because that sounded great.
He and Esau present.
That's pretty cool.
He and Esau present.
So I'm gonna play this one more time, and then compare again. But it looks like we got it. Like, it looks like this is what we needed. The problem is, though, is that it was a very different sample rate from what I expected. But that's good. Or it's, at least we know what it is now rather than my guess, which I had it to do on earlier. So good we checked it. That's what I really mean. Oh yeah, whoops. We still have all the voices muted in here, so let's go ahead and undo that. Yeah, there's that. And then we can just... we'll just let it fail and exit. Doesn't matter. It'll fail because it'll try to overwrite the dump that it just did. But it's open in Ableton, so it can't do that.
He and Esau present.
He and Esau present.
Great. Why does this not play stuff now? Oh, because we're still hacking the phase, aren't we? Yeah, that's fine. It shouldn't really hurt anything. This guy here. That would make sense. And the fact that it basically still sounded the same. I'll play it again just to be sure without that in there. But that basically says that, okay, we got enough of what we needed to understand. And then we don't even have to really reverse engineer the sample playback routine anymore. As long as we've seen that that's where it adjusts the timer.
He and Esau present.
He and Esau present.
Cool. The one in the emulator still sounds tinier to me, but I think it has to do with just the fact that this is being played like just as raw samples. There's also going to be some resampling happening in Ableton. They don't sound like they're different rates, at least, and that's kind of what we're after here. I was going to check one more thing, though, and that's basically I want to print out whenever the timer control is written, just to make sure that what we see in the code and what I'm thinking, like if it's just written those 2 times, right around when it writes the audio registers, that basically we get what we expect. I'll print out this stuff as well. Right. But yeah, this totally is info, which is exactly what we need more of right now.
T and E saw.
Now I cut it off in the middle there again, just to be sure that we got what we wanted. Okay, so here we go. Timer reload happened on 4, and then the timer fired. The 15 was written into this register. Then it wrote all the values, and then 19 was written. So actually, exactly what we expected is here. So now if we go back up to our notes up here, now the only difference is that this is actually 120 microseconds, right? Because that'll give us a sample rate of, right, which is what matches our output here. And I know that this wave output code is definitely correct, because it's the same one we used in the other thing. It's the same one we used when we had the emulator dumping wave. This has been tested. And I also remember checking the metadata after doing the Galactic Pinball stuff when the sample rates didn't match up to check that all the math and everything was correct, and this is definitely right. So cool.
T and E saw present.
So that's what we got out of this. And then also this information here. Timer reload is set to 4. Timer rate fires every 120 microseconds. We store 15 in the timer control. Output volumes to voice 1 volume through voice 5 volume, and then store 0x19 in the timer control, which is exactly what we're seeing here. And we've confirmed that that's all we actually need to do to actually get the sample out. So that's, I think, as deep as we have to go with this game. So what I'm going to do is I'm going to upload this to a gist really quick. And call it a night. I think this was as successful as we could have hoped. So there's the gist. And now we have more info. Cool. Yeah, thanks for watching, guys. I'm considering when I take apart my Switch to stream it. I don't know if I'll be very talkative because like my microphone and everything and my setup's all over here, but then my where I'm gonna do everything and take the pictures is over on a different desk. So if I'm too lazy to move it, sorry about that. But I am considering streaming. So if you guys are up around like midnight to 3 a.m. CET, then I may have that up, but we'll see. Anyway, again, emulator stream on Sunday. And beyond that, I will see you guys next time. So thanks again.